From the very beginning, Dorothea sensed her son was extraordinary. When Carl was just 2 years old, he surprised her by crawling up on the table where she was preparing soup. He pointed to the potatoes, counted the first few aloud, and then asked, "What comes next?" Dorothea, who had no education and could only count up to 6, could hardly believe her ears. As Margaret Tent wrote in her biography of Gauss, the Prince of Mathematics, Carl wanted to know. He demanded to know. She couldn't stop Carl's curiosity, and she didn't think she wanted to, even if she could. At age 3, Carl corrected his father, a stonemason, when he made a mistake calculating how much he owed his workers. Numbers fascinated Carl the way toys fascinate other children. At 7, Carl began attending his local elementary school in Brunswick, Germany. His teacher, Herr Wütner, didn't hesitate to whip unruly children, but Carl wasn't intimidated. He always knew the answers. One day, Herr Wütner assigned his students the task of finding the sum of all the numbers from 1 to 100, expecting it to take a while. A few minutes later, Carl wrote down his answer, 5,050. His teacher asked how he did it so quickly. Carl explained, pairing the smallest number, 1, with the largest number, 100, gave 101. The next smallest and next largest also gave 101. With 50 such pairs, the sum was simply 50 times 101 equals 5,050. The stunned teacher visited Carl's father to convince him his son needed to develop his abilities through advanced study. Carl's father valued manual labor and was reluctant, but he eventually agreed to let him study with Wütner's assistant, Martin Bartels. Carl's studies, though, were often cut short by sunset, as his parents couldn't afford candles. So Carl decided to build a makeshift candle out of a potato or turnip that he filled with fat and lit so he could read Leonhard Euler's famous algebra textbook late into the night. In this work, Euler observed that the number of solutions to a polynomial equation equals its highest exponent. X plus 2 equals 5 has only one solution, x equals 3, whereas x to the power of 2 plus 3x plus 2 equals 0 has 2 solutions because its highest exponent is 2. However, Carl noticed gaps in Euler's observation. He only accounted for real solutions, numbers that can be plotted on a number line, like -2, 0, 3, and 5, and ignored complex numbers. Take the equation x to the power of 2 plus 1 equals 0. Rewriting it as x to the power of 2 equals -1 reveals the problem. No real number squared equals -1. Carl rigorously proved that Euler's principle holds true for all polynomials, including those with complex solutions. He later reflected to a friend, "I believed then, as now, that some parts of mathematics need reinventing." Carl also studied Euclid's Elements, written around 300 BC, which laid the groundwork for geometry. But he questioned Euclid's fifth postulate, also known as the parallel postulate, which states, given a line and a point outside it, there is exactly one line through the point that is parallel to the original line. Carl realized this didn't hold true on curved surfaces. For example, on Earth, lines of longitude, in red, are not parallel because they converge at the north and south poles, even though they appear parallel near the equator. This realization transformed our understanding of space and led to the development of entirely new frameworks known as non-Euclidean geometries. Among these, hyperbolic geometry allows multiple lines to pass through a given point, all of which are parallel to the original line and never intersect. But Carl never published his work on non-Euclidean geometry. He feared backlash as Euclidean geometry was seen as the absolute truth at the time, and he hated controversy. When Hungarian mathematician Johann Bolyai published similar findings decades later, Carl remarked, "To praise Johann's fine work would be only to praise myself, since I discovered non-Euclidean geometry more than 20 years ago." Carl's tutor was so impressed with Carl that he introduced him to a local professor who arranged for the boy to meet the Duke of Brunswick, Carl Wilhelm Ferdinand. Impressed by the 11-year-old Carl, the Duke offered to fund his education, which his poor, uneducated parents could otherwise not afford. In 1795, Carl moved to the town of Göttingen to study at the University of Göttingen, one of the most prestigious centers of learning in Europe. While he loved learning languages there, easily picking up Latin, Greek, French, and English, his greatest passion was math. Carl proved that a regular 17-gon can be constructed using only a compass and a straight edge, a tool for drawing straight lines without any measurements. This was incredibly challenging as it required precise geometric techniques without the aid of modern tools. He wished to have a regular 17-gon engraved on his tombstone, But the stone carver refused, fearing people might mistake it for a poorly carved circle. While at university, he also solved a personal mystery: his birthday. His parents only remembered he was born on a Wednesday in 1777, the week before Ascension Day, which is 40 days after Easter. To find Easter, Carl broke the problem into steps using modular arithmetic, dividing 1777 by 4 to check the leap year cycle, by 7 to align the weekdays, and by 19 to follow the moon cycle for Easter, noting the remainders for each. Using these remainders, he plugged them into a formula to pinpoint Easter Sunday as March 30, 1777. From there, he counted forward 40 days to find Ascension Day and backtracked to the Wednesday before, his birthday, April 30, 1777. In 1798, Carl returned to his hometown of Brunswick after concluding that the University of Göttingen had nothing more to teach him. Instead of living with his parents, he rented a room to work in peace. Carl's father saw no value in his theoretical pursuits and had hoped his son would earn a living through physical labor. Carl defended his work, arguing that his intellectual efforts laid the foundation for mathematics and science. Not understanding and tired of arguing with his son, Carl's father walked away. They never spoke or saw each other again. The Duke, on the other hand, believed in Carl's potential and continued to support him financially. His generosity and patience paid off. Carl's efforts culminated in the publication of Arithmetical Investigations in 1801. The book included a rigorous proof of the fundamental theorem of arithmetic, which states that every whole number greater than 1 can be expressed uniquely as a product of prime numbers. This established prime numbers as the building blocks of all integers and reinforced their role as the basis of modern number theory. Carl dedicated his seminal work to the Duke. Your understanding and support over the last 13 years has made it possible. You believed in me and you enabled me to devote these years to the fruitful study of mathematics. I thank you heartily. Many in Brunswick resented the Duke's financial backing of Carl, failing to see the importance of his work. His genius was not yet understood by the wider public until he discovered a lost planet. In January 1801, Italian astronomer Giuseppe Piazzi discovered a small planet, Ceres, but could only observe a small portion of its orbit, just 9 degrees, before it disappeared from view. With no way to locate it again, Ceres seemed lost. Carl seized the challenge of predicting the dwarf planet's position. Using his mathematical brilliance, he developed a formula to calculate its orbit and determine where it would likely reappear. When astronomers rediscovered Ceres in December 1801, exactly where Carl had predicted, he became an instant celebrity, solidifying his reputation as one of history's greatest mathematical prodigies. His personal life also blossomed. Back in Brunswick, he'd visit his godfather's house where he met Johanna Osthoff. It took Carl a year to muster the courage to express his feelings in a heartfelt letter. I want to tell you how much I admire you. You are beautiful and charming. As far as I can tell, you have no flaws. I would like to ask you to be my bride if you could love me too. I am not rich and I don't have very much to offer you, but I believe I have enough for 2 modest people to live on. If you are willing to marry me, I would be true to you, and I would do my very best to support you and love you forever. Though Johanna admired Carl, she didn't think she was good enough for him. She was smart, but she wasn't intelligent enough to understand his work. But that didn't matter to Carl. He loved her for who she was. They married on October 9, 1805, when Carl was 28 and Johanna 25. He gleefully wrote to his close friend, the mathematician Wolfgang Bolyai, "I never expected to find such happiness." The following year, they welcomed their first son, whom they named after Giuseppe Piazzi, the Italian astronomer who had discovered the previously missing Ceres. Carl and Johanna lived happily until their lives were overturned when the Duke was wounded in a battle against Napoleon's troops and later died. When French troops occupied Brunswick, Napoleon instructed his generals not to harm Carl, on the advice of a French mathematician by the name of Monsieur Leblanc. Carl later learned that Monsieur Leblanc was actually Sophie Germain. Sophie had hidden her identity in her correspondence with Carl, fearing he wouldn't take a woman seriously. On the contrary, he expressed his delight to her. When I learned that the illustrious Monsieur Leblanc is in fact a woman, I was overjoyed. To provide for his family, which now included a daughter, Carl accepted a position as the director of the Göttingen Observatory. Though he also taught small groups of students, he found teaching tiresome and wanted to focus entirely on research. In 1809, he published one of his greatest works, which presented a detailed method for determining the orbit of a planetary object even with only a few observations. Today, his methods are still used to track satellites, predict asteroid paths, and guide spacecraft across the solar system. While analyzing errors in astronomical observations, he noticed discrepancies in measurements of celestial bodies' positions often followed a pattern. They tended to cluster around an average, forming a bell-shaped curve that would later bear his name. This concept is fundamental to any discipline that relies on data, including understanding IQ, demonstrating how Carl Gauss's work transcended mathematics. That same year, Carl and Johanna welcomed their third child. However, Johanna struggled with her health after the birth of baby Louis, and she worried as he appeared weak and struggled to nurse. A month later, Johanna passed away. A heartbroken Carl wrote to a friend, "I closed her angel eyes forever. I don't know how to deal with this." A few months later, baby Louis also died. A year later, Carl proposed to Mina Waldeck, a good friend of his late wife. He was honest about his feelings, writing to her, "You must understand, Fräulein Waldeck, that Johanna was the love of my life. No one will ever replace her in my heart, but you are a good, kind person. If you are willing to accept a different place in my heart, I would like very much to marry you and bring up a family with you." They married and eventually had 3 children of their own. In 1816, they moved into the new Göttingen Observatory, which included a residential wing as much of the work required nighttime observations. Carl's 74-year-old mother, who was immensely proud of her son, joined them the following year, 9 years after the death of Carl's father. She was a simple woman who didn't feel comfortable eating in her son's grand dining room and preferred to eat in the kitchen with the servants. In 1816, King George IV entrusted him with the monumental task of surveying the Kingdom of Hanover, a hilly region of approximately 15,000 square miles in northern Germany ruled by the British Crown. To accomplish this ambitious project, Carl employed triangulation. Starting with a precisely measured baseline, he calculated angles and distances to map the region accurately using a network of interconnected triangles, laying the foundation for modern mapmaking. The dense vegetation made it difficult to establish clear lines of sight. He and his team even cut down trees to create visibility between triangulation points. Recognizing the limitations of existing tools, Carl invented the heliotrope, an innovative device that used mirrors to reflect sunlight into a focused beam visible over long distances. By the early 1830s, the survey was nearing completion, allowing him to spend more time at home. However, heartbreak struck his family once again. His wife had become gravely ill with tuberculosis and was bedridden for several years. His mother had gone blind. Carl clashed with him and Mina's eldest son, Eugen, who aspired to follow in his father's footsteps in mathematics, but Carl believed he lacked the aptitude and insisted he study law. Frustrated, Eugen turned to gambling and drinking, amassing huge debts. The situation became so dire that he fled to America to escape his creditors. His departure devastated his mother, who passed away in 1831. Despite the grief of losing his second wife and now his son to America, Carl channeled his energy into his work, making groundbreaking contributions to the field of magnetism. Through meticulous measurements, he discovered that most of Earth's magnetism originates deep within its core rather than from surface rocks, and that the Earth as a whole is significantly less magnetic than a piece of steel. While he focused on understanding the Earth's magnetic field, we now know that this field extends far into space, forming a protective shield called the magnetosphere. This shield deflects solar particles traveling at over 1 million miles an hour, preventing them from stripping away the atmosphere and making Earth uninhabitable. In recognition of his contributions to the study of magnetism, the unit of magnetic field strength, the Gauss, was named in his honor. Throughout his life's challenges and triumphs, Carl Gauss remained deeply loyal to his mother, who lived to the remarkable age of 97, passing away in 1839. He followed her 16 years later, passing away on February 23, 1855, at the age of 77. Just 3 days before his death, Carl calculated the exact number of days he had lived, true to his mathematical nature. Carl Gauss was aware of his extraordinary brilliance, but he credited his success not solely to innate talent, but to his relentless hard work. Quote, "If others would think about mathematical truths as deeply and as continuously as I have, they would make my discoveries." It's a reminder that success in math or anything comes from dedicating time to learning and understanding the concepts. And that's exactly where Brilliant can help. Brilliant's interactive math courses are designed to help you no matter your skill level. Whether you're looking to build and use formulas to solve real-world problems, sharpen your spatial reasoning, or dive into advanced mathematical concepts, Brilliant gives you the tools to succeed. What I love about Brilliant is how interactive it is. It's not about memorizing, but learning by doing, which has proven to be 6 times more effective than just watching videos. Right now, I'm exploring their programming courses where you can familiarize yourself with Python and start building programs on day 1 using their built-in drag and drop editor. There's something for everyone, including data science content and AI. You can try out Brilliant for free by clicking on my custom link in the description, brilliant.org/newsthink. That's brilliant.org/newsthink for a free 30-day trial. Plus, you'll save 20% on an annual premium subscription, giving you access to Brilliant's thousands of interactive lessons. Thanks for watching. For Newsthink, I'm Cindy Palm.